Just like you had properties of derivatives, you have properties of integrals, and a lot of them we've talked about already. Some interesting ones. If the derivative is the area under the curve from A to B, and if we even just think about the fundamental theorem of calculus part 2 that we were introduced to, if you take the antiderivative, then the actual area is really simple. You just have to plug in A and you just have to plug in B, subtract the two, and you're fine. Now, using that fundamental theorem of calculus, if your letters got switched, would you agree that this is now just this? And I don't know if you've ever noticed that if you did something like 7 minus 3 and then you did 3 minus 7, one of them is a positive number, one is a negative number, but it's the same number. That is why number 2 is true. If you wanted to find the area from A to B and it was a positive number, if you reversed it and found it from B to A, then you would get the same number, but you would have a negative sign in front. If you have, I like this one. It really makes sense if you think of a picture. Okay? Integral from A to B means that you are figuring out the area under the curve from A to B. If we introduce some value C in between, does it make sense to you that the area from A to C plus the area from C to B would be the same as what you started with as the area from A to B? So a lot of our integral properties, when we think about what they mean, are really common sense. And integral property number 5 is the same as the derivative property. For adding and subtracting, not multiplying and dividing, you can just do the integral of each part set. So with that, we get to play around with our integral rules. They tell you the following information. You know the area from 0 to 2 is 4. You know the area from 2 to 5 is 12 on F. And on G, you know the area from 0 to 2 is negative 3. And from 0 to 4 is 6. So what area would you have if you had this? So we need to use our properties and break this up, rearrange it so that we get these 4 things that we know. And then we could replace them. Well, adding and subtracting, those I could do separate. That's property number 5. What's really nice about doing those separate is, can you see that this one already matches with this one? This doesn't match. However, I could pull that 3 out, because that's a property of integrals. You can pull a constant out in front. What's nice about that is now this matches perfectly with this. So I can replace the purple with 4, and the green box I can replace with negative 3. So I'd have 3 times 4 minus a negative 3. And that's equal to 15. So we use our properties, a little bit of manipulation, and get values. So try the next 4. They're kind of fun. I put up the answer for number 2 just so you could check it. Does it make sense that if you go from 2 to 2, you would have no area? And there's the answer for the 3rd one. All right, here's the 4th one. Okay. A little bit of transformations from grade 12. F of x plus 3 would be a translation of 3 to the left. Okay, I can bring the 1/2 out in front, but does it make sense to you that going from -3 to -1 is the same as going from 0 to 2 of the graph move 3 to left? Visualize this. You know your original function. I don't know, let's say it's this, from 0 to 2. You have this area was given to us to be 8? No, 4. There we go. It's 4. We'll do it that way. We were told that that was 4. Now, f of x plus 3 just says you take this original thing and move it, all of it, not that part. Oh yeah, I'll just... move it 3 to the right. Does the area under here change when I move it 3 to the right? No, it's still going to have an area of 4. So if the graph had been moved 3 to the left, I said right, I moved it left. If that graph was moved 3 to the left, the area stays the same. So we can imagine, okay, I move it back 3 to the right, well, 3 to the right, then move that up to 0 and that one up to 2. That matches up with the value that I have. There, same picture, idea. Just moved 3 to the left. So we just have to integrate. So properties say we can integrate both of these separately. And I am fine if you do not write that step in your own work. And you just go directly to integrating this one, integrating this one. I wouldn't be mad if you did one set of brackets. This would be perfectly fine. Whenever you're adding and subtracting, you can integrate them separately. So you could do one set of brackets, or you could do it separately. What happens with the definite integral? We find the antiderivative first, then you plug in the top number and evaluate, and then subtract, plugging in the bottom number. So if you did them separately, you would have 1/4 minus 0, and here you would have e minus e to the 0 is 1. If you had it this way, you would have, plug in 1, you'd get 1/4 plus e, and over here you'd have 0 plus 1. Combine that together, and you get e minus 3/4. So, fundamental theorem of calculus part 2, we find the antiderivative, write it in a square set of brackets and keep the bottom number and the top number. Plug in the top number and subtract, plug in the bottom number. And I have to marvel at what we just did a little bit, okay? X cubed plus e to the x. I'm sorry, I have no idea. Is that a graph that you've memorized? Is that like x cubed plus e to the x? There's our graph. I hit graph, probably doesn't, oh, there it is. Maybe, and from 0 to 1, we just calculated this area from 0 to 1 on a very weird curve, really quickly and extremely accurately. We're more accurate than our calculator. Our calculator right now has it as a value. So I can, anytime I solve this, I can store that answer as x, so that I can see that I get 1.96. We calculated it exactly to be e minus 3 over 4. Check this out. Exact same number. Really? Go back. Not complicated math well, super complicated math, but knowing how to do it, no really crazy calculations. You knew all your derivatives. You know all your integrals. Plugging in the value is not hard. And yet, what we just found was equivalent to adding up thousands of rectangles with Riemann sums. Quickly, easily, and more efficiently, because this takes out any of the error. That's really, really powerful. If you like finding areas, I guess. So sometimes there's a constant in there. Taking that constant out can help your brain trigger recognition. Do you recognize the 1 over x? Do you recognize the 1 over x as the natural log? Natural log of the absolute value. Technically, the absolute values wouldn't be needed here because we're only plugging in positive values. Plug them in. Mental math. Do you remember what natural log of e is? 1. Do you remember what natural log of 1 is? It's just 5. That also is kind of crazy. Because 5 over x, right? 5 over x is not hard to graph. But then if someone said, hey, can you just tell me what, if you went up to from 1 to 2.718281828, and wanted to find that area, what does it look like to you? And like, oh, it looks like 5. It's perfectly 5. That's crazy. So first look. Looks not very nice. Do we have any integral rules like a quotient rule? No. So this, in this form, is not integratable. I don't know if that's a word, but I just made it up if it is. No, that made no sense. Okay. But I could take each one of those and divide it by 4x and break them up. And if I break them up by dividing each one by 4x, each of those individually is ones that you could do. Me personally, though, I don't think I would write all of those integrals over and over again. Would you be okay to put it in one set of brackets from 1 to 2? Plug them in and subtract. Here they're still all separate, which is okay. Four natural log of 2 minus 11 over 3. To 12 plus 12 to 16. Agreed? So if I move this whole thing over to this side, do you see that you would have the 3 to the 16 all by itself, like I have down here? I'd have a 3 to the 12, but instead of plus, I would have, I'm just sort of visualizing here, I would have 3 to the 12, but then I would have minus, and I have the 12 here, and the question mark down there. See how that's related? Now with the minus sign, I could change it to a positive and flip those two numbers. So the answer is going to be 16. That's how I would think about this one. I would think about rearranging it so that it matched up with my numbers. But technically, this does match up with the formula. It just feels wrong. Because you like to pick C in between. But even if the C is not in between, it still works. And it works because of the thinking that I showed down below. So here we have a piecewise function. It's the 2x squared from 0 to 5, and it's just 20 from 5 to 7. Calculate each of those integrals separately. And again, you can just write the answer down probably pretty quickly. And then I want to ask you, can you get the 40 without calculus? So the second area, the 5 to 7 of the 20, it has an area of 40. Can you think about that, visualize that, and get that answer without calculus? Because what does that graph look like? Right, 5 to 7, 20, and the graph is just a straight line. Can you visualize this green area? It's a perfect rectangle, right? The height is 20. The width is 2. Should make sense that it's 40. Beautiful that the calculus gives you the same answer, right? And most of us are going to, like, when I draw it, it's like, that was really quick. That would have been easy to do. But when we get into calculus mode, we'll probably do it this way. But it's always good to have that in your back of your head, sort of like, well, what actually is happening here? Maybe there's an easier way. Maybe there's something that I can see. Right? The 2x squared, the 250 over 3, no. Calculus is the best way to do that. What are we going to do with that absolute value? Take out our purple sheet. Do we have that absolute value at all on our purple sheet? Oh no. What do? Multiple choice on the exam? We guess. No. We can figure this out. Okay. Visually, can you picture it? X minus 3 is your absolute value graph moved 3 units over. There it is. We are trying to find the area from 0 to 4. Oh. Oops, I'm looking at this and I'm like, I think I could do this without calculus. They look like triangles to me. Pretty simple. So if I was problem solving, okay, And this is the part where the level that you guys are at, our problem solving says, I have trouble with the question technically right now because of how it's written. What does it mean graphically? What does it mean algebraically? How can I break this up? How can that help me? Okay? Now, if I wanted to continue algebraically, absolute values can be written as piecewise. You have two lines here. One with a negative slope, one with a positive slope. Whenever the x values are bigger than or equal to 3, inside would be positive, meaning you wouldn't need the absolute values. It would just be x minus 3. But whenever the x values were less than 3, the inside would be negative, and the absolute value would make that negative number positive. Algebraically, we can make a negative number positive by just multiplying by a negative. So the ability to write an absolute value as a piecewise function means we can break up this integral into two pieces. But now that I've drawn the graph, I'd be like, I think I really just want to do area of triangles. Okay? Base times height divided by 2. You see that this area is going to be 1, 9. 3 times 3 divided by 2. 9 divided by 2 for that side. And this is 1 times 1. 1 half. 9 halves plus 1 half. I think we're going to get 5. I'm hopeful. But we did the algebra way, and now we've got our integrals. Plug in our numbers. Oh, we get 5. But we're supposed to be learning calculus. So don't look at my graph and figure out the areas in that simplistic way. If we could? No? Quick, let me know. Using the following graph, which consists of lines, segments, and a semicircle, evaluate each definite integral. Let's just look at this and notice the shapes. There I have a triangle. I can find area of a triangle, base times height divided by 2. Are you okay that this is going to be 3 times 2 divided by 2? This area is 3. Area of a semicircle is going to be half of this blue part here. Half of a circle. Pi r squared. The circle would be pi. The whole circle would be pi 1 squared, which is just pi. Half the circle would be pi over 2. Do you see that that blue part is below the x-axis? So its area would be represented as negative pi over 2. Purple triangle. 1 times 3 divided by 2. 3 over 2. I'm going to just do this also in purple because it's identical. And in between, this rectangle in orange has an area of 6. If we would go from -4 to -1, from our picture now, easy to see that we would get 3. From 2 to 1, well, from 1 to 2, our area would increase by 3/2. So from 2 to 1, it would be -3/2 or -1.5. One to 5 of 2f of x. Now I'm not actually going to double that, but I'm just going to pull my 2 out in front, and adding up those parts, 6 plus 1.5 plus 1.5 will be 9, so I'll get 2 times that 9, which will be 18. And if I went from -4 all the way to 5, this is 9, this is 3. I have to subtract the pi over 2. 12 minus pi over 2. So actually labeling the things on the graph at the beginning really made all of this math quite easy. We didn't have to refigure things out as we're going. 2 to 4, that one, or sorry, 4 to 2, so that'll be -6. -4 to 1 of the absolute value. What does an absolute value do to a graph? Well, absolute value makes something positive. To a graph, it would take any part of your graph that's negative and flip it up. So now, going from -4 to 1, I would have this 3, but now this -pi over 2 would get flipped up, and it will be 3 plus the pi over 2.